With the publication of the final report in July 2012, some 3 years after the accident, the BEA felt confident in their understanding of what had happened to Air France 447. However, in circumstances such as these, it's often the why which proves more challenging and potentially far more controversial. In an effort to do just that, part of their investigation focused on previous industry incidents which closely mirrored the events of June 1st. In total, 13 similar incidents of lost airspeed were uncovered. Amazingly, although dating back to 2003, the most recent event had occurred only 10 days prior to the accident. In that incident of May 21st, 2009, an A330 operated by the Brazilian carrier TAM, en route from Miami to Sao Paulo, was in the cruise of flight level 370 at Mach 0.8 in moderate turbulence with an outside air temperature of minus 45 degrees centigrade. The crew subsequently reported that they had noticed an abrupt drop of the indicated outside temperature and observed St. Elmo's fire across the cockpit windshields, which was quickly followed by the loss of air data information. The indicated airspeed on the captain's instruments dropped by 200 knots before subsequently regaining 40 knots of that lost speed. At the same time, the recorded pressure altitude dropped by 300 feet. About 1 minute later, the first officer's airspeed indications began to fluctuate, with both autopilot and autothrust disconnecting. The captain took over and began to fly by reference to the standby instruments, which still appeared to be working normally. Pitch inputs to the left side stick were recorded, resulting in the aircraft pitching up to an altitude of 7 degrees. As a result, the airplane climbed almost 1,000 feet before being returned to flight level 370. The flight control laws reverted to alternate law and remained as such until after landing. The rudder travel limiter likewise deactivated and remained deactivated for the remainder of the flight. Aside, ECAM displayed the nav ADR disagree message. The crew, utilising the standby instruments, were able to restore primary data within 5 minutes, after which re-engagement of both autopilot and autothrust proved successful. The airplane reached Sao Paulo without further incident and landed safely. The NTSB, or the US National Transportation Safety Board, reported that a similar incident had happened to a Northwest Airbus A330-300 on June 23rd, a month earlier, over the East China Sea. In this, the second incident, the aircraft was en route at flight level 390, just entering Japanese airspace in daylight, about 50 nautical miles southwest of Kagoshima. The sky was mostly clear, with occasional isolated areas of rain and cloud tops of about 41,000 feet. Outside air temperature was minus 50 degrees centigrade, way too cold for liquid water at that altitude. The weather radar, however, showed heavy precipitation below the aircraft, with light precipitation, perhaps ice crystals, being painted by the weather radar at their level. Entering the tops of the clouds, the aircraft encountered light turbulence with winds of about 30 knots. About 15 seconds later, the crew experienced moderate rain on the windshield. Similar to the previous experience of the TAM crew, the Northwest crew also noticed a sharp drop of the indicated outside air temperature, followed by the loss of the air data information. This manifested itself in the disconnection of autopilot and autothrust, along with the loss of altitude information and the rollback of indicated airspeed on both sides to 60 knots. The flight control laws reconfigured to alternate law as ECAM generated a number of associated warnings and alerts. The captain, taking control, manually flew the aircraft the shortest possible route out of the weather. The airspeed indicators returned after about 60 seconds, with the aircraft returning to normal law and facilitating re-engagement of the autopilot. However, this lasted only briefly, and the events repeated themselves, this time the anomaly lasting for a further 2 minutes. Finally managing to clear the weather, system operation returned to normal, with the exception of the flight control laws, which remained in alternate law for the remainder of the flight. Despite all, only 5 knots of airspeed had been lost throughout the entire episode. Flight 008 subsequently landed safely in Tokyo Narita, without further incident. In the final case study, an Etihad A340-600, on February 2nd, 2013, 6 months after the final report was published, while en route from Abu Dhabi to Melbourne, Australia, 35,000 feet, over the Indian Ocean and about 900 nautical miles west-southwest of Singapore, encountered turbulence and the sudden onset of heavy precipitation. The aircraft airspeed indications on the captain's PFD reduced from 270 to 76 knots. The standby airspeed decreased from 280 to 142, with the first officer's indications being largely unaffected. The autopilot and autothrust automatically disconnected, and the flight control laws changed from normal to alternate. Briefly, the airspeed indications normalised, and the flight control laws reverted back to normal law. As seen previously though, this recovery was only transitory. The airspeeds again dropped, with the resultant reconfiguration back into alternate law, which was maintained until after landing. The inability to re-engage either autopilots or autothrust gave rise to operational issues which precluded the flight from continuing to its destination. Subsequently, the commander sought and received clearance to divert to Singapore, where the aircraft made a safe landing sometime later. So what had the BEA learned from these combined 13 events? With regard to the environment, it was noted that all events occurred between flight level 340 and 390. The air masses concerned were highly unstable and characterised by powerful convective phenomena. The relative temperature of these air masses was characteristically warmer than standard, sometimes by up to 10 degrees centigrade. Crews reported that they had not observed significant radar returns for their selected flight path, but had identified active zones nearby or at lower altitude. 3 crew reported having heard or observed what they identified as rain or ice. All the events occurred in IMC, Instrument Meteorological Conditions. The recordings of the total or static temperatures revealed increases of 10 to 20 degrees during the event, in some cases with the increase starting before the airspeed anomalies were observed. Turbulence was always recorded and reported, with levels felt by the crew varying from light to strong. With regard to the aircraft, the autopilot disconnected in all cases with no intervention from the crew. The disconnection of the autopilot was accompanied by the disappearance of the on-side flight director, and sometimes by the off-side flight director for a variable period of time. In all the cases studied, the flight directors reappeared during the event. In certain cases, this reappearance was recorded simultaneously. In 7 cases, an autopilot was re-engaged during the event. In 2 of these, the re-engagement occurred even though the 2 speeds were consistent with each other but erroneous. The autothrust disconnected in 10 cases, leading to the activation of the thrust locked function. In 5 of these cases, this function remained engaged for more than 1 minute, indicative perhaps of the startle these crews would have experienced. In 1 case, the crew had disconnected the autothrust and commanded the thrust corresponding to turbulence penetration speed, indicative again perhaps of some procedural confusion between this specific procedure and that of the unreliable speed condition. In 2 cases, the autothrust did not disconnect and the flight directors did not disappear. With the autothrust engaged, recordings of engine RPM parameters revealed fluctuations in thrust of between 48 and 100%. In 12 cases, the flight control laws changed to alternate law until the end of the flight. In 1 case, this transition was temporary. In the context of speed anomalies, these can be characterized by 2 distinct signatures, either intermittent drops or spikes, or a drop followed by a levelling off for a continuous, more prolonged period of time. These speed anomalies were accompanied by an instantaneous increase in indicated static temperature and in total temperature when it was recorded, and a fall in indicated altitude, particularly on the 330-200. The lowest speeds recorded were less than 100 knots. The maximum recorded duration of continuous invalidity of indicated speed was 3 minutes and 20 seconds. When the speed values calculated by the standby instruments were recorded, the signature and/or duration of their erroneous values showed differences from those noted in the recordings of the speed display on the captain's side. When considering crew reaction, the aircrafts remained within the flight envelope during these relatively short events, with variations in altitude being contained to within about 1,000 feet. There were 5 cases of deliberate descent, including one of 3,500 feet. These descents followed a stall warning. 4 crews did not identify the unreliable airspeed situation. In 2 cases, the crews concluded that there was an inconsistency between the angles of attack. In the other 2 cases, the crews considered that the speeds were erroneous rather than unreliable. For the cases studied, the recorded flight parameters and the accounts given by the crew did not reveal any application of the memory items from the unreliable speed procedure, nor the procedure itself. The reappearance of the flight directors in the PFD suggests that no disconnection inputs were made on the FCU. The autothrust had been disconnected before the anomalies began in one case. In the other cases, either the autothrust remained engaged or the thrust lock function remained active for several dozen seconds before manual adjustment of the thrust was undertaken. In summary, therefore, generally these types of anomaly resulted in the autopilot disconnecting, the flight directors disappearing, the autothrust changing to thrust lock, and the flight control laws changing to alternate law. The pilot flying prioritized flying tasks and the aircraft's flight path, maintaining a cruise attitude or descending to increase the margins for manoeuvre within the flight envelope. The decision to descend may also have been decided as a result of the stall warning being triggered. The reappearance of the flight directors on the PFD, when 2 airspeeds are calculated as similar, prompted some crews to promptly engage in autopilot. However, although the magnitude of these speeds may be the same, they may be erroneous and low and could cause the autopilot to command flight control service movements that are incompatible with the aircraft's actual speed. In those cases where the autothrust was automatically disconnected and the thrust lock function activated, the absence of an appropriate manual adjustment of the thrust levers in order to rectify the frozen thrust condition may generate a risk that the existing relationship between pitch and power is unsustainable, particularly when this disconnection occurs when the initial engine thrust value is low. 9 recorded cases of stall warning activation were noted. All the warning activations can be explained by the fact that the aircraft was in alternate law at cruise Mach number while being G-loaded by the turbulent prevailing environmental conditions. Only once was the warning attributed to distinct input on the controls. In all 3 case studies, the respective investigating authorities cited as a probable cause the brief and temporary blockage of the pitot probes in cruise flight, most likely due to ice crystals aloft, leading to erroneous airspeed indications and airplane automation degradation. Contributing to the incidents were design features of the Thales AA pitot probes, which left them more susceptible to high-altitude ice crystal icing than other approved pitot probe designs. Therein lies the second piece of the puzzle. Was it a deficiency with the aircraft's pitot probes themselves which allowed the blockage to occur in the first place? Simply put, was it a case that the pitot probes on Air France 447 simply weren't up to the job? As far back as 2001, there were issues with ingestion of ice crystals and/or water with a specific model of pitot probe manufactured by Goodrich. For simplicity's sake, let's identify this probe as the GR model. The solution at the time was mandatory replacement of this specific probe with an alternative. The choices available were either an upgraded model of the same product, for our purposes classified as the HL probe, or a completely different probe manufactured by a competitor, Thales, designated as the AA probe. This mandatory replacement was to have been carried out within a defined period of time, which would close on December 31st, 2003. The issue now becomes relevant to Air France as the operator takes delivery of its first A330 in December 2001. Incidentally, on delivery, the aircraft has already been fitted with the new Thales probe at the time of manufacture. Some years later in 2007, prompted by earlier incidents of water ingestion on their A320 fleet, Air France decided to incorporate a flight with unreliable airspeed scenario into its 2008-2009 training program. In designing the necessary training scenario, it was decided to script the event around the takeoff and initial climb phase of flight, which was deemed to be adequate to allow crews to practice the necessary drill. In reality, however, the procedure for dealing with such an eventuality immediately after takeoff is fundamentally different to managing the same scenario at altitude, where terrain is not an immediate threat. Thus, although gaining valuable experience in managing the problem, crews never received simulator exposure as to how this event might unfold during the cruise phase of flight. In September 2007, following measured speed inconsistencies on the A320 during periods of heavy precipitation or icing, Airbus published a service bulletin which recommended the replacement of the Thales AA probes with an updated BA version. The bulletin indicated that the newer model performed better in both cases of water ingestion during heavy rain and severe icing conditions. However, due to the absence of any reported incidents on its long-haul fleet, in the case of the 330-340, Air France decided to replace the AA probes with the BA model only in the event of a failure on the line. Between May 2008 and March 2009, 9 incidents of unreliable airspeed were reported by Air France pilots across its 330 and 340 fleets. All had occurred in the cruise. In 7 of the reported cases, the stall warning had been momentarily activated, and subsequently, after the accident, 6 additional events came to light which had not previously been reported through the safety reporting system. During late 2008, Air France asked Airbus to investigate the root cause of these events and for possible solutions. They also queried whether a move to exclusively using the Thales BA probe would improve the situation. Airbus replied that the most likely cause of the problem was obstruction by a rapid accumulation of ice crystals, and that based on current understanding, the BA model of probe was unlikely to make a significant difference. Air France alerted Thales about the increasing number of observed problems with icing at high altitude, following which the manufacturer began its own internal technical analysis. At this moment in time, the autumn of 2008, despite the increasing number of reports being received, Air France maintained the position that there was no immediate threat to flight safety. Despite this, they considered it wise and prudent to disseminate information to the pilot body at large in relation to these observations and their probable cause. This was done through routine safety bulletins from the Safety Office during early November of that year. Also that month, Airbus revised the earlier 2007 service bulletin. As in the earlier release, this version mentioned the improvements that could be achieved through installation of the Thales BA probe, specifically in relation to water ingestion, but critically no longer made reference to icing conditions. Furthermore, they said that there was no solution which would totally eliminate the risk of probe icing, but that all 3 variants of probe certified for use on the 330 not only satisfied, but exceeded all necessary regulatory requirements. At the end of March 2009, about 2 months before the accident, Air France experienced 2 additional events involving temporary loss of airspeed indication, including reports from the A330 fleet. On April 3rd, in light of these new occurrences, Air France once again asked Airbus to find a definitive solution. On April 15th, they responded by stating that studies had shown that the issue with icing involving ice crystals was a new phenomenon, not considered in the development of the Thales BA probe. But, regardless, this model probe appeared to offer significantly better performance in relation to unreliable airspeed indications at high altitude. Airbus offered to assist with an in-service evaluation of the product, and subsequently, on April 27th, 32 days before the accident, an internal technical document was drawn up within Air France to mandate replacement of all current probes on the A330 and 340 fleets with the Thales BA design, it being considered the best possible candidate of all manufactured probes at the time. The first batch of BA probes arrived at Air France on May 26th, 6 days before the loss of 447, with the first modification being completed 2 days before the accident. Ironically, the accident aircraft itself was scheduled for modification upon its return to Paris. As of November 2009, 5 months after the accident, Airbus had identified 32 cases of loss of airspeed events which had occurred between November 2003 and June 2009. Airbus attributed these events to the possible destruction of at least 2 probes by ice. 11 events occurred in 2008 and 10 during the first 5 months of 2009. 26 incidents occurred on aircraft with a Thales AA probe as fitted on 447. 2 occurred on aircraft fitted with the Thales BA probe, and 1 on an aircraft fitted with the Goodrich HL probe, the original alternative replacement to the AA probe way back in 2001. Subsequent and extensive wind tunnel testing with large concentrations of ice crystals were able to duplicate the occurrences in a controlled environment. Of all the probes tested, the Goodrich model proved the more capable of dealing with the severe environmental conditions under examination, and was thus ultimately chosen as the definitive replacement probe for the aircraft. Inevitably, as with any aircraft accident, the spotlight will at some stage fall on the crew training and competence. In this context, the fundamental cornerstone of crew performance, and identified as industry best practice, is the concept of CRM, or Crew Resource Management. CRM is defined as the utilisation in the cockpit of all available resources, equipment, procedures and people to ensure the safety and efficiency of flights. That being the case, there's a deliberate and significant focus on human factors and how to mitigate the inevitable errors which each and every one of us is prone to making. Air France, as with many other operators at the time, introduced specific and tailored CRM training at various key points of a pilot's career progression. For example, with initial recruitment into the company, and then again at upgrade to command, with annual refresher modules in between. Of note, however, was the BEA's observation that no specific additional CRM training was provided, nor indeed required by regulation, for first officers before being released to operate in the relief commander role. Specifically, in their final report, the BEA commented, "The operators training program does not give co-pilots the opportunity to systematically develop the mindset needed to perform the role of relief captain aboard flights with augmented crews. This lack of CRM training specific to the role of a relief captain could impair the synergetic response of a crew consisting of 2 co-pilots. Such a crew may therefore be less well prepared and able to implement cooperative management of an unexpected situation in the mid and long term." So although the first officer's ability to execute and resolve non-normal procedures was routinely covered during visits to the simulator, the higher level management of such events and their resultant consequences was brought into question. Furthermore, the arbitrary manner in which Air France procedures allowed for nomination of the relief commander further contributed to the dysfunctional situational management on the flight deck of 447. On the night in question, Robert in the left-hand seat was considerably more experienced than his fellow First Officer Bonan in the right. Despite the inference by Dubois before leaving the cockpit that Bonan, as PF, would automatically assume the role of relief commander, this very difference in experience between the 2 co-pilots quickly resulted in Robert naturally taking over as abnormal situation developed. Although not creating any specific conflict between the 2, this takeover led rapidly, after the autopilot disconnection, to the inversion of the normal hierarchical structure in the cockpit. The leadership role switched to Robert without this command function being formally and explicitly transferred. With regard to procedural training, Air France had incorporated an exercise relating to loss of indicated airspeed into their training syllabus for the year 2008-2009. But again, this exercise was scripted around an occurrence shortly after takeoff and not in the cruise. In fairness to Air France, however, at the time most operators were likewise somewhat remiss in their approach to high altitude training. Not solely in the context of this particular failure, but in relation to general overall manual handling of the aircraft at altitude and the associated aerodynamics. Indeed, such handling exposure in conjunction with downgraded flight control laws was largely unheard of and certainly not what have been described as common practice. Furthermore, in the context of stall recovery, prior to the loss of 447, the published procedures for stall recovery underemphasised the importance of angle of attack reduction, with some manufacturers' checklists actually stipulating a target pitch attitude for recovery. Most pilots were left with the impression that it was possible to power one's way out of trouble, minimising altitude loss in the process. Whereas this might well be possible in many cases, particularly at low level, it avoids the fundamental aerodynamic principle that stall is an angle of attack issue, not a speed issue, and that altitude considerations are largely secondary to reducing the angle of attack. Again, traditional training programs would have focused on low-level events, not occurrences in the cruise, which was the case not only in Air France, but across the entire industry at the time. Fidelity issues with training simulators meant, and is still largely the case today, that aerodynamic modelling beyond the point at which the wing stalls is unrepresentative. As such, pilots were, and largely still are, trained to recognise and react to an approaching stall. It is true to say that once 447 had actually entered the stall, the aircraft's behaviour and handling characteristics would have been nothing either Bonan or Robert had ever seen before. In other words, airlines, manufacturers and regulators at the time, be it deliberate or otherwise, simply had no focus on manual handling issues at high altitude. Stall recovery procedures were ambiguous, and simulator data packages on aircraft handling characteristics beyond the stall were incomplete. In conclusion, the BEA, after an exhaustive investigation lasting over 3 years, made the following recommendations. In relation to general operations at high altitude and aviation's potential exposure to environmental threats, they recommended to EASA, the European governing body for aviation, that studies should be undertaken with the aim of accurately assessing the composition of cloud masses at high altitude. To date, I'm unaware of whether this recommendation has been acted upon. From a technical perspective, the crew never formally identified the stall situation, perhaps in part as information on angle of attack is not directly accessible in the cockpit of an A330. By design, the angle of attack in cruise is close to that value which will trigger the stall warning, should the aircraft be in any other flight control law other than normal. Under these conditions, at altitude, manual handling can bring the aircraft to high angles of attack, such as those encountered during the event. As a statement of fact, it is essential in order to ensure flight safety that the angle of attack be reduced when a stall is imminent. It was thus deemed that a direct cockpit readout of the angle of attack would greatly aid crews in rapidly identifying the current aerodynamic situation of the aircraft and thus facilitate a more efficient and timely recovery response. Consequently, the BEA recommended that EASA and the FAA evaluate the relevance of requiring the presence of an angle of attack indicator directly accessible to pilots on the flight deck. To date, at least with the Airbus types, no progress has been made in this regard. Aircraft handling in the longitudinal axis, in a reconfigured law, is in general very similar in sensation and response to flying in normal law. Nevertheless, exiting the flight envelope is possible without longitudinal pilot inputs on the side stick, as a result of lost protections and the absence of positive longitudinal stability. It was considered that current training does not adequately draw crews' attention to the precise nature of a control law reconfiguration and associated reduced levels of protection, nor the importance and/or necessity to monitor the trajectory and the primary parameters under such circumstances. In general, the complexity of modern aircraft and their peculiarities require appropriate initial and recurrent training courses. Consequently, the BEA recommended that EASA ensure the integration in type rating and recurrent training programs of exercises that take into account all of the reconfiguration laws. The objective sought is to make recognition and understanding easier for crews, especially when dealing with the level of protections available and the possible differences in handling characteristics across the entire flight envelope. EASA's subsequent mandate of type-specific upset and recovery training for pilots has very much resulted in a greater level of awareness and understanding of this particular subject matter, although the level of resources and commitment can differ greatly from one operator to the next. The BEA concluded that the successive failure messages displayed on ECAM did not allow the crew to make a rapid and effective diagnosis of the aircraft's failure situation, specifically in relation to any definitive alert highlighting blockage of the pitot probes. ECAM presentation never fully allowed the crew to make the connection between the messages that appeared and the procedures which needed to be applied. This despite the fact that the design philosophy of the ECAM is that it should facilitate the analysis of failure situations and subsequently allow for these failures to be managed. It is true that several systems had identified the origin of the problem, but subsequently only generated failure messages related to the consequences on themselves. Consequently, the BEA recommended that EASA study the relevance of having a dedicated warning provided to the crew when specific monitoring is triggered, in order to facilitate comprehension of the situation. No action has been taken on foot of this recommendation, and ECAM logic remains as before. As a statement of fact, the crew did not deactivate the flight directors and did not call out any changes in FMA modes. Whether they were aware of their appearance and disappearance is uncertain. However, that said, as they reappeared, it is conceivable that the crew were not conscious of the reconfigured pitch and roll commands, as reading and assimilating the displays of the FMA in dynamic and stressful conditions is not instinctive or natural. It was the BEA's opinion that requiring an action from the crew to re-engage the flight directors would, firstly, demonstrate consistency with regard autopilot and auto-thrust re-engagement logic following a disconnection event, and secondly, stimulate a check on the modes and the consistency of the commands presented at the time of re-engagement. Consequently, the BEA recommended that EASA require a review of the redisplay and reconnection logic of the flight directors after their disappearance, in particular to review the conditions in which an action by the crew would be necessary to re-engage them. Further, even if it was not established for certain that the crew followed the orders from the flight directors while the stall warning was active, the orders from the crossbar presented inappropriate guidance, contradictory to what was necessary in order to recover from the situation. It is quite plausible, therefore, that the flight director commands at the time may well have confused or troubled the crew. Consequently, the BEA recommended EASA require a review of the functional or display logic of the flight director so that it disappears or presents appropriate orders when the stall warning is triggered. Although the re-engagement logic has been amended so that the flight directors will now reappear in the same modes as were displayed prior to their disappearance, this reappearance is still an automatic function and does not require a conscious reselection by the pilot, as was the BEA's recommendation. As for guidance approaching the stall, nothing has changed. Flight director logic in this regard has remained unchanged and does not display pitch guidance towards recovery from the approach to stall or indeed the stall itself. The stall warning is described as being a combination of the oral warning, the illumination of the red master warning lights on the FCU, and the visual red and black pole or VSW on the speed tape, if reconfigured away from normal law. Illumination of the red master warning light, however, from simulator training exposure, is more commonly triggered by some other level 3 warning, an engine fire for example. That being the case, in the absence of the red and black VSW bar on the speed tape, the only element that presents unambiguous clarity and approach to stall is the oral warning. It was the BEA's belief that definitive symbolic visual information combined with the oral warning would doubtless improve pilot perception and general situational awareness. Consequently, the BEA recommended that EASA determine the conditions in which, on approach to stall, the presence of a dedicated visual indication combined with an oral warning should be made mandatory. As a result of the recommendation, more recent aircraft off the production line now incorporate a visual trigger on the PFD, where the word stall is displayed in large red letters in order to visually grab the pilot's attention. On the 330, when airspeeds are below 60 knots, the stall warning is no longer available, even though it may be beneficial for it to be available at all times. Consequently, the BEA recommended that EASA require a review of the conditions for the functioning of the stall warning in flight when speed measurements are very low. To date, I am unaware that any modification has been made to the stall warning logic. In the context of crew proficiency and training, the investigation brought to light weaknesses in the two co-pilots. The inappropriate inputs by the PF on the flight controls at high altitude were not noted by the PNF through an absence of effective monitoring of the flight path. The stall warning and the buffeting were not identified either. This was probably due to a lack of specific training, although in accordance with regulatory requirements. Manual aircraft handling cannot be improvised and requires precision and measured inputs on the flight controls. There are other possible situations leading to autopilot disconnection for which only specific and regular training can provide the skills necessary to ensure the safety of the flight. Examination of their last training records and check rides made it clear that the co-pilots had not been trained for manual aircraft handling of approach to stall and stall recovery at high altitude. Consequently, the BEA recommended that EASA review the content of check and training programs and make mandatory, in particular, the setting up of a specific and regular exercise dedicated to manual aircraft handling of approach to stall and stall recovery, including exercises at high altitude. The startle effect played a major role in the destabilisation of the flight path and in the two pilots' understanding of the situation. Initial and recurrent training as delivered at the time did not promote and test the crew's capacity to react to the unexpected. Indeed, most training exercises were identified as repetitive and well known to crews. This fact failed to facilitate the evaluation of resource management skills outside of this context. All of the effort invested in anticipation and predetermination of procedural responses did not exclude the possibility of a real-life event of fundamental surprise to the crew, their preparedness for which as a result was lacking. The rapid increase in crew workload in an unusual and unexpected situation led to the degradation of the quality of communication and coordination between the pilots. Consequently, the BEA recommended that EASA review the requirements for initial, recurrent and type rating training of pilots in order to develop and maintain a capacity to manage crew resources when faced with the surprise generated by unexpected situations. Furthermore, a second recommendation suggested that EASA ensure that operators reinforce CRM training to enable acquisition and maintenance of adequate behavioural automatic responses in unexpected and unusual situations with a highly charged emotional factor. Difficult as it is to do, most operators have made efforts to introduce surprise events into simulator training details and generally to revise the content of the respective CRM material. The crew of Flight 447 did not associate the disappearance of the speed information and the resultant ECAM messages with the unreliable airspeed procedure. Although the crew had experienced the particular failure of airspeed indications in the simulator previously, the technical limitations of the simulator, whose fidelity is satisfactory in most cases, did not lend itself to accurately reproducing this particular scenario well. Exercises were often contrived and translated poorly into the real world. The same could be said for simulator stall modelling, which for the vast majority of devices is unrepresentative once the aircraft actually enters the stall. Fidelity limitations of the simulator will also inhibit the crew's ability to appreciate fully the true effect of startle and the inappropriate reflex actions on the controls which can occur as a result. Thus, the pilot's ability to possibly avoid, identify and recover from such a situation is compromised. Consequently, the BEA recommended that EASA modify the basis of the regulations in order to ensure better fidelity for simulators in reproducing realistic scenarios of abnormal situations, and furthermore, again act to ensure the introduction into the training scenarios of the effect of surprise in order to train pilots to face these phenomena and to work in situations with a highly charged emotional factor. After the autopilot disconnection, while the aircraft was stable in cruise, several pilot inputs significantly degraded its kinetic energy. The rapid exit from the flight envelope was not anticipated by the pilots, nor was it understood. In the absence of any reliable speed indications, understanding of the overall physics of flight at high altitude could have considerably helped the pilots to anticipate the rapid degradation of the situation. The same applies to the overspeed phenomena that has evolved with modern aircraft. Consequently, the BEA recommended that EASA defined recurrent training program requirements to make sure, through practical exercises, that the theoretical knowledge, particularly in flight mechanics, is well understood. Subsequent mandatory upset prevention and recovery training has resulted in an increased understanding of the subject matter amongst pilots across the industry. The investigation showed that the captain left to take his rest without having clearly nominated the PF as his relief. The flight crew, consisting of 2 co-pilots, thus inherited a certain strategic vagueness after his departure, which was reinforced by a lack of tailored in-house training for first officers expected to fill the role of relief commander. Though the distribution of roles between the 2 co-pilots probably did not seem ambiguous to them, it did nevertheless pose a problem. In fact, the BEA questioned the rationale for designating Bonan as relief captain, purely on the basis of him having been nominated as PF for the leg home, as his overall experience was much less than that of Robert. Consequently, the BEA recommended that EASA and the DGAC, the National French Aviation Authority, define additional criteria for access to the role of relief captain so as to ensure better task sharing in case of augmented crews. At the time, regulations required recording of the flight parameter display on the left-hand side of the cockpit only. Some parameters essential to the analysis of the conduct of the flight were therefore lacking, in particular those displayed to the pilot in the right seat, for example speed, altitude, attitude, position of the flight director crossbars, etc. Consequently, the BEA recommended that EASA and the FAA make mandatory the recording of flight director crossbar positioning relating to the conduct of the flight, displayed on the right-hand side instruments in addition to those displayed on the left side. Finally, analysis of both the flight data recorder and the cockpit voice recorder provided information that was essential to the understanding of the event. However, it was difficult to reconstruct the indications that were available to the crew on their respective instrument panels, especially the instructions given by the flight director crossbars when they reappeared. It was also impossible to see whether there had been any attempts to re-engage the autopilot, for example. A view of the instrument panel would complement the information provided by the FDR and CVR and would make it possible to confirm the indications that were available to the crew and the crew's response to such indications. Numerous recommendations have already been made on the subject over the past number of years, without any real progress having been made. Consequently, the BEA again recommended that ICAO, the International Civil Aviation Organization, require that aircraft undertaking public transport flights be equipped with an image recorder that makes it possible to observe the whole of the instrument panel, and that at the same time ICAO establish very strict rules for the readout of such recordings in order to guarantee their confidentiality. To date, no progress has been made in this regard. So in conclusion, what did cause the loss of Air France 447? There's a very valid saying out there which states that there are 2 sides to every story, and in that regard 447 was no different. In fact, what I hope I have demonstrated is that with regard this and most aircraft accidents, there are usually many sides to a given story. Aircraft accidents are seldom the result of one single occurrence, but rather many underlying events which interact with each other, conspiring to produce often catastrophic outcomes. What if the ITCZ hadn't been active on the morning of June 1st? What if the pitot probes on the accident aircraft had been modified in Paris prior to departure? What if Captain Dubois had remained on the flight deck for another 5 minutes? What if previous training had mentally prepared Bonan and Robert to deal with the shock of a sudden unexpected event? What if they had been armed with a greater understanding and experience of high-altitude handling characteristics? What if the true implications of flight control law reconfiguration had been understood? What if their previous CRM training had specifically focused on the skill sets each would need to successfully execute the role of relief commander, a role which they were infrequently exposed to? What if previous simulator training had focused on the characteristics of approach to stall at high altitude, and above all else prioritised the importance of reducing angle of attack in such circumstances? What if the design of the aircraft failed to allow a situation where a counterintuitive nose-down input on the side stick triggered a stall warning, while a nose-up input silenced it? What if the design of the aircraft failed to facilitate removal of speed information from the PFD at very low speeds? What if? In truth, the reason why Bonan continued to input nose-up commands will never be known. However, what is also true is that the story of 447 is not his alone. My own personal belief is that, startled by the sudden and inexplicable disconnection of the autopilot, Bonan was thrust into the management of a situation he was ill-prepared for. Reconfiguration to alternate law 2 made the aircraft extremely sensitive in roll. Immediately impacted by the convective environment they were traversing, his efforts to stop the aircraft from rolling uncontrollably simply left him with little or no cognitive ability to monitor or predict the aircraft's trajectory and pitch, hence the climb. The collective inability to monitor, evaluate, recognise, and ultimately recover reflects not only on them but also on the support structure around them. Manual handling these large jets at altitude is a completely different proposition to flying at low levels, where the atmosphere is more dense. But in 2009 and the years beforehand, the requirement for such handling experience was largely deemed unnecessary. In this regard, Air France was not unique. Operators around the world were similarly remiss in their approach to the subject matter. It simply wasn't an issue for either the airlines nor the regulators. A vacuum had existed for years, which by good fortune had never been exposed in anger, until the night of June 1st, 2009. To say it was an accident waiting to happen may be somewhat dramatic, but in reality, that's not too far from the truth. Aviation, however, if nothing else, is resilient and demonstrates a unique desire and ability to learn from its own experience and mistakes. The aviation world of 2009 is not the same aviation world we live in today, and this is in no small part due to the lessons learned from 447. If there is any solace to be gained from such a tragedy, then perhaps this is it.